Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to lesson 14. This is modeling relationships with a line. So in the last lesson, they gave us the equation, but now we are going to, in this lesson, we're going to create a linear equation that fits the data. Okay, so classwork example 1 says using a line to describe a relationship. Kendra likes to watch crime scene investigation shows on television. She watched a show where investigators used a shoe print to help identify a suspect in a case. She questioned how possible it is to predict someone's height from his shoe size or shoe print. To investigate, she collected data on shoe length in inches and height in inches from 10 adult men. Her data appear in the table and scatter plot below. So someone with a shoe length of 12.6, their height was about 74 inches, and so on and so on. Shoe length, height, X. Shoe length, X, height, Y. Okay, so is there a relationship between shoe length and height? So I look at this data, and I'm trying to determine whether or not I could draw a line through the data that would best represent the shape of these dots. So if I drew this line, say like right here, does it look like these dots are sort of close to that line? And I would actually say yes. It's not real strong. If this dot was a little lower and this one was lower and this one was lower and these three were a little bit higher and closer, that'd be a stronger relationship, but there is still a relationship here. So number one, yes, it looks like there is a relationship between shoe length and height. 2 says, how would you describe the relationship? And do men with longer shoe lengths tend to be taller? So if we look at this data, you could say, well, this person had a shorter shoe length and they weren't as tall. And these people over here had longer shoe lengths and therefore they were taller. So as shoe length increased, so did the height. So let's say that. All right, so as shoe length increases, height tends to increase. Men with longer shoe lengths tend to be taller. Page 2 brings us to example 2, using models to make predictions. When two variables, x and y, are linearly related, you can use a line to describe the relationship. You can also use the equation of the line to predict the value of the y variable based on the value of the x variable. For example, the line y equals 25.3 plus 3.66x might be used to describe the relationship between shoe length and height. Whether x represents shoe length and y represents height, or where I should say, not whether, where x represents shoe length, y represents height. To predict the height of a man with a shoe length of 12 inches, you would substitute 12 for x in the equation of the line and then calculate the value of y. So in this equation, you'd have y equals 25.3 plus 3.66x equals 25.3 plus 3.66 times 12. So what they had done here, obviously, is substituted in 12 for the x. And then when you take 3.66 times 12 and then add 25.3 to it, you get 69.22. So you would predict the height of 69.22 inches for a man with a shoe length of 12 inches using this linear equation. So exercises 3 through 7, here we go. So exercises mean try on your own, pause the video, and then come back and see if you did it correctly. Okay, so here we go. Number 3, below is a scatter plot of the data with two linear models. Y equals 130 minus 5x, that is the black line. And I know that because minus 5x is a negative slope, so it's going down as x goes greater, y gets smaller. That's the black line. And y equals 25.3 plus 3.66x. So since it's a positive slope, positive 3.66, then I know that that is the blue line. As x increases, y increases. Which of these two models does a better job of describing how the shoe length x and height y are related? Explain your choice. So what you want to do is look at these dots. So are they fairly close to the black line, Or are they closer to the blue line? Does the blue line represent them better? And if I were to draw a trench, if you would, here is an area in between, and the blue line is kind of parallel to these purple lines, and all my data falls within those, so I would say that is a better fit. So as if I tried that with the black line and I went this way, then these are much more spread out and they don't fit so well. So it looks to me like it is the blue line, and that would be the one with positive slope, so I would choose this one. Okay, so putting that into words, let's say the line of y equals 25.3 plus 3.66x is a better choice because as shoe length increases, height tends to increase. Number 4, one of the men in the sample has a shoe length of 11.8 inches. Okay, so let's identify that before I move any further. Get some practice here on reading graphs as well. So 11.8 is not quite 12. Here's 11.75. So it could be this point here, or it could be this point here, seeing how that kind of lines up with 11.8. Okay, and let's see, inches and a height of 71. So 71 is here, so now we know which one it is. Okay, so now we're talking about this point right here. All right, circle the point in the scatter plot in exercise 3 that represents this man. So there we have it. It is this one. This one would be 11.8 possibly, and like 65 or 64. So it is definitely this point. Okay, page 3 brings us to problem number 5. And it says, suppose that you do not know this man's height, but you do know that his shoe length is 11.8 inches. Well, height is y, and shoe length is x. If you use the model, y equals, I'm going to rewrite it here, 25.3 plus 366x, 3.66x, and then we substitute in the given, and then we can find the unknown. So they're telling us x is 11.8, so I'd say y equals 25.3 plus 3.66 times 11.8. Now I can do this manually, but let's just save some time for the computer and save some time for the video and use my calculator to do this. So I put 25.3 plus 3.66 parentheses, which means times in the calculator, 11.8. So if I put that in the calculator and hit enter, I get y to equal the height of 68.488 inches. Okay, so the predicted height would be 68.488 inches. And then it says, what would you predict the height to be if we use this model? So now I'm going to switch to this model, and I'm going to write y equals 130 minus 5x. Substitute in the y, 130 minus 5 times 11.8. So then y is going to equal, and then I use my calculator, 130 plus, just kidding, minus 130 minus 5 parentheses 11.8, and hit enter, and I get 71. Okay, so in using the first model, the man's predicted height would have been 68.488 inches, and using the second model, the man's height would have been a prediction of 71 inches. They're both very close, but an inch and a half is an inch and a half. Number 6, which model was closer to the actual height of 71 inches? That model a better fit to the data, and explain your answer. Well, which model was closer to the actual 71? Well, we got actually 71 from this, so it was the model y equals 130 minus 5x was closer. But that's not the better model because the other one was closer. So if we go back, we were using the equation where 11.8 and we got 71. So that's 11.871. That's right here. So we were right on that line, but that was not the better line for all of the data. It was better for that point, but overall, the blue line would have been a better fit for all of the data. So let's say that. So we'd say the model y equals 130 minus 5x was closer to the actual value, but that's not a better model because y equals 25.3 plus 3.66 is closer to more points. Okay, so sometimes a model might be better for one point, but for the group is what we're looking for. Number 7, is there a better way to decide which of the two lines provides a better description of a relationship, rather than just comparing the predicted value to the actual value for one data point in the sample? Okay, this is wordy. The better line, or the line with the best fit, is the one in which the distances from the points to the line are as short as possible. Highlight a few of the points and the distances from the points to the line. Highlight the vertical distances from various points to the line to show students how the value of residuals help us evaluate a line's fit. So what they're saying is, if I come back here and let's use green. So what they're telling us to do, I want to do a line, and let's do line green. So if I pick this point here, what they're saying is draw vertical lines. Like so. And what we want is the shortest possible line for the whole group. So if we draw all these vertical lines, and what that is called the then we take the average. Okay, so that one would look like, so you get the idea, we're just taking vertical distances, the distance y is, the y value is from the y value of the prediction. That's all we're really doing. So this here shows that that's a really short line. This one's pretty short. That one is 2. So is this one. This one's a bit longer. So is this. And this one's very long. But it's a better fit than if we use the other. And let me just take the time to show you that. And I will use red for these. So what they're saying is, now if we drew a perpendicular distance to the black line. No, I don't want to do that. It's got to be vertical. And the line doesn't go far enough to show this, but it would probably be more like up here. So you see now how much longer these red lines are. These are right on it, but the other ones, look how far this one is, and then this one is pretty far here, and this one is even farther, and then this one would have to come all the way down to there. So as you can see, the red lines are longer than the green ones were if you added up all the lengths and took their average. The reds would be a greater average, so that's not as good of a fit. Hopefully that was more understandable doing that. So the green lines are definitely shorter. And that's what number 7 says. Now example 3 says residuals. One way to think about how useful a line is for describing a relationship between two variables is to use the line to predict the y values for the points in the scatter plot. These predicted values could then be compared to the actual y values. For example, the first data point in the table represents a man whose shoe length was 12.6 inches and his height was 74. So let's go back. 12.6, 74. Let me get rid of these lines. Okay, 12.6 comma 74 was the point. So 12.5 is here. 12.6 will be over here somewhere. 74 is up here. It is this point right here. All right, so that's the point they're talking about now. Let's go back to the problem. And it says, for example, the first data point in the table represents 12.6 and 74. If you use the line y equals 25.3 plus 3.66 to predict this man's height, you would have gotten 71.42. So if I come back here, it would have been 71.42. if we used this equation here, which is how far are we from the actuals, what they're going to ask now. Okay, so then it says his predicted height was 71.42 inches because his actual height was 74. You can calculate the prediction error, there's a new term, by subtracting the predicted value from the actual. So what they're saying is, here's the actual value. The predicted value would have been that distance, would have been the value on the line. So it would have been this point here. So what we're doing is we're taking the actual minus the predicted and getting the difference, and actually what it is the length of this difference here, of these 2 points. How far is this point from the prediction? And when they did that, 74 minus 71.42, okay, I labeled that wrong. This is 71.42, and this is the point 74. So we took 74 minus 71.42, and the difference was 2.58. Okay, so that was the prediction error, the distance from the actual value and the predicted value. Page 4 brings us to exercise 8 through 10. Number 8 says, for the line y equals 25.3 plus 3.66x, calculate the missing values and then add them to complete the table. Okay, so now I'm going to use the calculator. So there is a way to do this on this screen here. I would have to type in 25.3 plus 3.66 times, and then here's the 11.8 that we've already done. 11.8, and we got 68.488. So I can write that in there now. So it's 68.488, which would round to 49 if we're going into the second decimal place. All right, but I want to point out something to you, and then here's 11.8, or 12 point, no, that was 11.8. That was using the minus, we got 71. So we're not using this equation here, but what I want to point out to you is you could type this in manually every single time, or you can use the calculator to do it for you and fill this all in at once. So if you just put this equation in, y equals, so I pressed y equals, and then put 25.3 plus 3.66x into your y equals equation, and then I want to go to a table, so that's second graph. See, the table's in blue, so you use the blue button. Second graph brings me to the table, and it's asking what x is. Well, x is right here, and if I put 11.8, then it will tell me that's 68.488 or 49. Now if I want to do 12.2, I just put 12.2 here, and I don't have to type the equation in every time. It calculates it automatically. So that one is 69.95. Okay, and then 12.2 will be the last one. And again, we've already done that, so that is 12.2 is already on the screen there, so it's again 69.95. But I could type any one of these in here. Like here's a 12.6, let's just do 12.6 just to show you that it comes out to be what's on the screen. And 12, well, I did 126, let's go back up and delete that. 12.6, I missed the decimal, enter. 71.42, 71.42. Okay, so now we want to know the residual. So we're taking y minus predicted y, and we get a value. So 65 minus 68 is a negative 3. 71 minus 69.95 is 0.05. And here it's 68 minus 67.2, which would be 0.98. Okay, so there we finished filling in the table. Number 9, why is the residual in the table's first row positive, right here, and the residual in the second row negative? Well, let's look. The y height was 74 and the predicted was 71.42. So the y height was 74 and the predicted was 71.42. You subtract the 2 and it was positive because we are above the prediction line. Now let's go back to that and look at the second line. 11.8 gave us 65 and 68.49. 11.8 gave us 65 and now I forget. 65 and 68.49. 68.49 is here. So the difference is below the line, so it's negative. So if our dots end up underneath our prediction or less than our prediction, then the difference would be negative because we're taking this value minus that value and we're getting a negative value. This minus this would give us positive. Okay, so let's put that into words. So the actual value is larger than the predicted in the first row, so the difference is positive. And the second row, the actual value is less than the predicted, so the difference is negative. Number 10, what is the sum of the residuals? Why did you get a number close to 0 for this sum? Does this mean all the residuals were close to 0? So now they want to know what the sum of the residuals are. So I'm going to just go to my calculator and plug them in. 2.58 plus negative 3.49. So that'd be minus 3.49, or I can put that in parentheses. Negative 3.49 plus 0.05 plus a negative 0.76 plus, so I'm right here now, negative 0.95, parentheses, negative 0.95, plus 0.98, plus a negative 2.15, plus, now we're here, negative 0.95, plus 0.58, plus 2.51. So when we added up all of these residuals, it says what's the sum of the residuals? And we got negative 1.6. Okay, so I started looking at this closer and I figured that it would be closer to 0 than that. So I did some calculations and I figured out I made a mistake right here. Okay, so right there is not just 0.5. That would have been 70 minus 69.95. So I need to fix that. 71 minus 69.95 is 1.05. So if I take my total here and just add 1 to it, so I was off by 1, then I get negative 0.6. Okay, that I feel better with because it is closer to 0 and it should be. So the sum of the residuals was negative 0.6. This should be 1.05. Why did you get a number close to 0 for this sum? Well, you want to do the averages. So I would say the sum of the residuals is negative 0.6. The number is close to 0 because the positive and negative values of the residuals balance each other out. It's kind of like an average. Not all residuals are close to 0, and you just refer to the table to see that. Negative 3.49 is pretty far from 0. 2.15 negative. Positive 2.51, positive 2.58, they aren't all close to 0. So that does not mean they're all close to 0. Okay, number 11 through 13. When you use a line to describe the relationship between two number variables, numerical variables, the best line is the line that makes the residuals as small as possible overall. 11. If the residuals tend to be small, what does that say about the fit of the line to the data? So if residual is really small, the difference between actual and predicted is your residual. Actual minus predicted is residual. If you have a small residual, what does that mean? Okay, if the residuals are small, the points tend to be closer to the line. Okay, before going on to page 5, I want to explain the term least squares regression. So we're going to take the square of the residual because we don't want negative values. So what we're going to do is take areas of, before I was showing you in the graph here, and let me just clean this up, I was showing you the lines. So if I just were to draw a line like I did before to show how far away a point was from the line, then some lines are positive and others are negative because if you're above or below. But I'm going to take this one step further now, and if I create squares instead and start this square here, for instance, and drag it to there is a square. And if I do the same here, pick this point here and come up to there so that that corner is on the line and this one. So what I'm doing is, actually it should be bigger than that. I'm not just taking the point. I want to draw a square who has one length. The length of one side is the distance from that line. So this is a distance that's negative. But if I take this negative and then that's, so if this was -3, then this is -3, and a negative times a negative is positive, and that gives us an area of 9, if you will. And if I continue to do that for all of these squares, so if I make this square come over like that, and actually I'm still going to change this one because I don't want it overlapping, I just have to draw it the other direction. I want these squares to just simply touch the line, like this. Actually, no, I still want it to go over. Okay, so if it's under, so this would be to there. So what I'm doing is I'm making squares with the side length being the residual distance. Okay, so we're making all these squares. So what we're going to do is add up all the areas of the squares, so because it's positive, and then that gives us a prediction that's going to be a positive value. So if I go back to this table here now and put this here, what these are the squared values. And you can check these if you want, but I'm not going to do it right now. -3 times -3 is 9, but that 0.49 would bring it to 12. 2 squared, or 25 squared, is 625, so 2.5 would be 6.25, but this 8 over here makes it 6.6564, and so on. So these are all the squared values. So the most common choice for the best line is the line that makes the sum of the squared residuals as small as possible. So there's the column to the right in exercise 8 that calculates the square. Okay, so this is leading us to this question now. Why do we use the sum of the squared residuals instead of just the sum of the residuals without squaring? Hint, think about whether the sum of the residuals for a line can be small, even if the prediction errors are large. Can this happen for squared residuals? Okay, so if you just add all of the residuals, positive and negative residuals can offset one another, and you can get a small sum even if some of the residuals are big. Squaring the residuals gives positive values that still reflect how far the data points are from the line. So in other words, if you take this sum of that new column, what is the sum of the squared residuals from the line in the data in exercise 11? So if we go back here and now add all these up, what will we get? So let's do that. So we're going to take 6.6564 plus 12.1801 plus 1.1025 plus 0.5776 plus 0.9025 plus 0.9604 plus 4.6225 plus, oh, that 2 didn't, oops, I can't hit backspace there, all right, I need another 2 here, plus 0.9025 plus 0.3364 plus 6.3001 and hit enter. We get 34.541. So the sum of the squared residuals rounded to the nearest hundred is, okay, 35.54. Okay, 35 or 34.54. Let's try that again. 34.54. Okay, example 4. The least squares line, best fit line, the line that has a smaller sum of squared residuals for this data set than any other line is called the least squares line. This line can also be called the best fit line or the line of best fit or regression line. So there's lots of names for this meaning the same thing. For the shoe length and height data for the sample of 10 men, the line y equals 25.3 plus 3.66x is the least squares line. No other line would have a smaller sum of squared residuals for this data set than this line. There are equations that can be used to calculate the value for the slope and the intercept of the least squares line, but these formulas require a lot of tedious calculations. Fortunately, a graphing calculator can be used to find the equation of the least squares line. Okay, your teacher will show you how to enter data and obtain the equation of the least squares line using your graphing calculator or other statistics program. So I guess I will do that in this lesson. So exercise 14 says enter the shoe length and height data and then use your calculator to find the equation of the least squares line. All right, so we're going to enter the shoe length and height data. So let's go back to that table. So we are putting this in the calculator. Okay. Okay, so to do this, we're going to first clear our home screen. I'm going to go to y equals and clear that. And then I'm going to go to second table and clear those. I just like to have everything clear. Okay, so now I'm on my home screen. Everything's been cleared out. In order to enter this data in an XY table, you want to go to stat. And then you edit is just number 1 or just hit enter because it's already there. Okay, I arrow up to L1 and I hit clear and arrow down and all those values are gone. Arrow over and then up to L2. Do not hit delete, that deletes the whole column from the spreadsheet and we don't want to do that. So we're going to hit clear, not delete. Bringing it down and now everything is blank. So now I'm going to enter the X's. 12.6, 11.8, 12.2. Okay, to save time in the video, I entered it all. And notice I'm on the last value, 11.8. Okay, so 11.8, 11.8. And this tells us right here how many rows we've used now. So this is the 10th row, so that's our 10th value. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, just want to make sure that there's the right number. So there's all my values. They don't show them all on the screen. It's not big enough. And now I'm going to enter the Y's. So I'm going to enter 74, 65, 71. I'll just do it quickly here, and then we'll come back. Okay, so now they're all entered. And as you can see, if I move up to my last one, there are 10 values. You need to make sure that these are equal. If you have an X and there's no Y, or if you have too many Y's and not enough X's, you're going to get an error and it's going to say mismatch. So there has to be a Y for every X. Alright, so now if I scroll back up to the top, and I did fix that typing error by the way, so there it is. There's all of our values in L1 and L2. Now we're going to hit stat, calculate, and we're doing a linear regression, so it's number 4. So I press stat, and then this button here. So let me do that again. Clear, we're back here. Press stat, arrow over to calculate, and then number 4 is linear regression, so I just hit 4. And then L1 is X, L2 is Y. Make sure that that says that, and just enter through and hit calculate. So there they give us our equation. So y equals ax plus b, so this would be y equals 3.657 x plus 25.27 blah blah blah. This is 25.3. 25.27 rounds to 25.3. This is 3.66. 3.657 rounds to 3.66. So there's our equation. I can take this one step further now and just put it, rather than trying to write this down and then go back and type it in here. You know how you do Control C and Control V in your calculator, you can, or computer? You can do the same in your calculator. It's a little bit more difficult. You go to y equals. Now I press the vars button. And I want statistics, which is 5. And I want EQ. And I want to put number 1, that regression equation, in. And that just put that whole equation in there without rounding, which makes it more accurate. Now if I go to y equals, actually I got to hit enter first. Okay, now if I arrow up and turn my plot on right here, and then if I zoom statistics, zoom stat, and hit enter, it will show this table right here. Okay, it shows this table right here, all of those dots. See these 3 dots here? There's those 3 dots there. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. It duplicated this table, and it showed the blue line going through the data, not the black line. So there it is. So if you need to go through those steps, you might think it's a very confusing, lengthy procedure to do linear regressions, but trust me, I've been doing this for years with students. Once you do a few of these, it becomes second nature, and it's actually quite simple. You get it. Okay, so where does that leave us here? All right, so enter the shoe length, and we did that. Did you get the equation? The slope and y-intercept here have been rounded to the nearest hundreds. Did we get this equation? And the answer is yes, we did. Okay, page 6, number 15 says, assuming that 10 men in the sample are representative of adult men in general, what height would you predict for a man whose shoe length is 12.5 inches? Okay, so basically what they're saying is you take that equation and you plug those values in. So our prediction equation was, which is right here, I'll just steal it from there, y equals 25.3 plus 3.66 x. Y equals 25.3 plus 3.66 times 12.5. And then I get y equals, I'm just going to use my calculator now, which just shut off. Okay, and I'm going to go to second table, and my equation's in y equals. So I had to put that in here for this to work. So you had to go through that vars thing. So now if I go to second table and type in that 12.5, it will calculate the value for me. And it was 70.99. All right. And now keep in mind though, I'm using at exact, I did not round. But if I go to the home screen and I put 25.3 plus 3.66 times 12.5, I get 71.05. Okay, so this is the importance of rounding. So we rounded to 0.366 and 25.3, where if I go to my equation here, it's 3.657024793 blah blah blah. They didn't round to 0.6. So when I go in my calculator after entering this, I get a more accurate answer. So 70.99 is actually the prediction, not 71.05. But if you just use this equation, you're going to be off by 6/100ths, which isn't a whole lot, but it is an amount that you're off. And then it says, what would you predict for a man whose shoe length is 11.9? Again, if I just put 11.9 in this equation, so I'll do that. Go back to the home screen. And then if I just hit second enter, I don't have to enter this whole thing over again. Then I arrow back and just change the X to 11.9. And all these little shortcuts make a big difference. If you get really familiar with this calculator, if you go on to take a timed test like an SAT or an AP exam and you are timed, the better you know your calculator, the quicker you can do. You're not wasting time calculating arithmetic, if you will. So this came out to be 68.854, which is 68.86. So for this one, it would have been a prediction of 68.86 inches. But if I go into my calculator and put that 11.9 in my calculator without rounding, I got 68.795, which rounds to 68.80. See the difference? Okay. So once you have found the equation of the least squares line, the values of the slope and y-intercept of the line often reveal something interesting about the relationship you're modeling. The slope of the least squares line is the change in the predicted value of the y value associated with the increase of the 1 in the value of the x variable. So it's basically rate of change. Okay. 16. Give an interpretation of the slope of the least squares line y equals 25.3 plus 3.66x for predicting height from shoe size for adult men. Okay, the slope is 3.66 for every 1 inch increase in a man's shoe length. You would estimate an increase of 3.66 inches in height for every inch. That's what that means. Okay, the next one. The y-intercept of a line is the predicted value of y when x equals 0. When using a line as a model for the relationship between two numerical variables, it often does not make sense to interpret the y-intercept because an x value of 0 may not make any sense. Explain why this does not make sense to interpret the y-intercept of 25.3 as the predicted height of an adult male whose shoe length is 0. Okay, hopefully that's obvious to you that it does not make sense. Okay, so we would say the y-intercept is 0, 25.3. Since x represents shoe length, it is impossible for the shoe length to be 0 inches when a man is 25.3 inches tall. Okay, that would mean he wouldn't have feet. Okay. Page 7 brings us to the end of lesson 14. Review the lesson summary and go to your problem set.